Hello, I'm Eric Taylor, and this is an abbreviated version of our oral presentation for the CVPR workshop, Minds versus Machines. I take a moment to acknowledge my co-author, Shashank, who made an equal contribution to this paper. How would you explain AI decisions if you couldn't look inside the black box? In this example, we have AlexNet taking an image as input and responding with its top 5 best guesses at what the image contains. Most XAI techniques depend strongly on knowing the details of the model and being able to interact with and inspect its nuts and bolts. We are proposing that it is important to be able to produce explanations without knowing anything about the model itself. How would you explain AlexNet's decision if you only had access to the input and output? In this paper, we propose measuring response time, which is available from outside the black box, to make inferences about the model's decision making. We looked at a model using conditional computation with auxiliary intermediate classifiers. These are classifiers that are appended to the model at intermediate layers. The model is allowed to quit early if a confidence threshold or computational budget is reached. The logic is simple. If a decision depends on features composed in deeper layers, it should go through more layers before reaching the confidence needed for an early exit. Response time should correspond to feature complexity. In our first experiment, we compared response times to images from the popular ImageNet dataset versus ObjectNet, which contains images at odd angles and viewpoints and is much harder for models trained for object recognition. We measured response time as the system clock time elapsed across the entire range of confidence thresholds. In other words, we measured how long the model took to reach a decision given all possible values of minimum confidence. If one classifier was insufficiently confident, the forward pass would proceed to the next one until a classifier produced a response with adequate confidence. The first panel on the left here shows a representative input from ImageNet on the top and ObjectNet on the bottom. Both are chairs, but one is more canonical than the other. And I've highlighted ImageNet in blue and ObjectNet in red, and we'll use those colors going forward. The second panel contains a graph showing the response time on the vertical axis required to reach the confidence threshold on the horizontal axis for 5 randomly selected chairs from both test sets. The values of k equals 1 through 5 on the right vertical axis show the response time for each of the 5 auxiliary classifiers. This pattern forms a step function because the response time for any given classifier is always constant. If that classifier is insufficiently confident, the response time plot bumps up to the next plateau. Ideal performance in this case is a backwards L shape, where the first classifier will be adequately confident for all threshold values. The third panel shows the mean response time for the 2 test sets across all images. The inset shows the grand mean. So we can see that response time analyses reveal large differences in processing difficulty between the 2 test sets. This pattern of results is a proof of concept for using response time analyses to document task difficulty, but we can't make very strong claims about feature processing because there are many differences in the input between ImageNet and ObjectNet. To do that, we need input with more carefully controlled features. Let's take a look at the scene grammar dataset designed for experiments with human subjects, or CGRAM for short. For our second experiment, we turn to the human phenomenon of scene grammar. Humans use object-object and object-scene relationships to guide visual attention and to make sense of scenes. It turns out that we are very sensitive to these high-level relationships. For each scene in the dataset, there are 4 versions of the image with different semantic or syntactic scene grammar violations. Here's what those look like. In the top left, we have the control image with consistent scene grammar. Nothing is wrong or out of place. In the bottom left, we have an image with inconsistent semantics. Clocks do not normally appear in dish drying racks. In the top right, we have an image with inconsistent syntactics. So the pot lid normally appears in the kitchen scene, but it does not normally appear floating on the front of the dishwasher. It's out of place. The dataset also contains images with both kinds of violations. So here we have a semantic and syntactic violation. And here are the results. The left panel again shows our step plots for the response time at all confidence thresholds for a forward pass using each of the 4 images from one scene as input. This is an illustrative case, and in this example, we can see the image with consistent scene grammar, the blue line, shows better performance. It can reach a higher confidence threshold by remaining at the fastest classifier than when it processes images with inconsistent scene grammar. On the right panel here, we take the mean response time across all 62 scenes. We see the fastest response time for consistent images. and slower response times for images with inconsistent semantics. We confirm these patterns with the repeated measures ANOVA. Interestingly, the response time profile for consistent images appears to deviate from the rest in the first and second classifiers, which means that the features MSDNet struggled with in the images with inconsistent semantics were not confidently processed prior to the earlier classifiers. Using these response time plots, we can start to make inferences about where in the model different features are processed. In addition to predicting when response time profiles should differ, we should also be able to predict when differences should not emerge. CGRAM comes with clones of every image where the critical object has been removed, so no clock, no pot lid from our previous examples. Because these images have no scene grammar violations by definition, their response time plots should collapse on top of each other. Thanks for watching this abbreviated version of our oral presentation, and be sure to come watch the full thing on Monday.